In this session, we define an exact differential equation and then state the condition for testing that a differential equation is exact, and then give some steps on how to solve exact differential equation. And in the subsequent class, we'll do examples on how to solve exact differential equations. So let's start by defining an exact differential equation. So first order differential equation of the form, or that can be written in the form m dx plus n dy equals to 0, such that m dx plus n dy equals to partial f partial x dx plus partial f partial y dy for some arbitrary function f is called an exact differential equation. So our first order differential equation that can be written in this form, m dx plus n dy equals to 0, such that m is the same as partial f partial x, n is partial f partial y, for some arbitrary function f of xy is called an exact differential equation. So the key objective in solving exact differential equation is to find this arbitrary function f of xy. So the test for this equation to be exact, so let's call this equation 1. For equation 1 to be exact, then if you take partial m, partial y, you must always get partial n, partial x. So this is a necessary condition for 1 to be exact, that partial m partial y equals to partial n partial x. So we can give examples. One, so this will be classified the following as exact or non-exact equations. So the first equation is sine of y plus y cos x dx plus sine of x plus x cos of y dy equals to 0. Now here, so m is given by sine y plus y cos x. N is given by sine of x plus x cos of y. So remember the general equation is m dx plus n dy equals to 0. And we test that partial m partial y equals to partial n partial x. So in this case, partial m partial y, this will give us cosine of y, and then this will give us cos of x when you differentiate this with respect to y, and then partial n partial x will be, this term will give us cos of x, this term will give us cos of y. And clearly, you can see that partial m partial y, which is the same as cosine of y plus cosine of x, is exactly the same as partial n partial x. So since partial m partial y equals to partial n partial x, so the equation is exact. Hence, the given equation is exact. Number 2, x squared y dx plus 5xy squared dy equals to 0. Now here, m is x squared y, and n is given by 5x y squared. So this means partial m partial y is x squared, and this means partial n partial x is given by 5y squared. Now, okay, partial m partial y, which is x squared, is not the same as partial n partial x, whose value is 5y squared. So since partial m partial y is not equals to partial n partial x, the equation is not exact. Number 3, we have 2xy cubed dx plus 1 plus 3x squared y squared dy equals to 0. Here, our m is given by 2xy cubed, and our n is 1 plus 3x squared y squared. Now from m we get partial m partial y. So partial m partial y would be given by 3 times 2 is 6, and then x y squared. And then from n we get partial n partial x, which will give us 2 by 3 is 6 x y squared. Now clearly, partial m partial y is the same as 6x y squared, which is partial n partial x. Hence, the equation is exact. Next problem. Number 4. Sine x cos of y plus e raised power 2x dx plus cos of x sine of y plus tan of y dy equals to 0. So here, m is sine of x cos of y plus e raised power 2x, and n is given by cosine of x sine of y plus tan of y. So this means partial m partial y, where the first term will give us sine of x, second term will give us 0, so just sine of x. And this partial n partial y, partial x, will give us, so remember this was, so this is negative when you define the value of partial m partial y. So in this term, sine x is a constant, so cosine of y, when you differentiate, you get negative sine of y times sine x. So sine x sine y. This doesn't have a y, so it will be 0. Partial n partial x You differentiate this cos, you get negative sign, and then times this sine of y. So this would be 0 because there's no x variable here. So clearly, partial m, partial y is minus sine x, sine of y, which is partial n, partial x, and the equation is exact. So that is simply the way we test whether a given differential equation is exact or not exact. So you rewrite the equation in the form m dx plus n dy equals to 0, and check that if you differentiate m partially with respect to y, you get partial n partial x. So this is the main thing that we do on testing for exactness. Once the equation is in this form, identify your m, identify your n, and then check that when you differentiate partially m with respect to y, it's the same as partial n partial x. So if that is true, then the given equation is exact. Now, I'll briefly go through the steps on how to solve exact differential equations. So algorithm, or steps for solving an exact differential equation. So remember, an exact differential equation, so it's an equation of this form, whereby the value of m is the same as partial f partial x, and the value of n is partial f partial y for an arbitrary function f. And so that arbitrary function f is what we are interested in finding. So the first step, we assume that m is the same as partial f partial x, and n is partial f partial y. Please note that already m dx plus n dy equals to 0 has obeyed the test for exactness. That is, you have completely shown that partial m partial y equals to partial n partial x. We have to first test whether the equation is exact before now you start these steps. So this is already assumed that the condition for exactness is holding for this given equation. So once this condition holds, then assume that m is partial f partial x and n is partial f partial y. Number 2, integrate m with respect to x. Remember, m is partial f partial x. So integrate m with respect to x. And then in this integration, you add an arbitrary function of y, say g of y. Remember, when you are carrying out partial derivatives, so if you are doing with respect to x, any function of y just takes the role as a constant in the normal single-valued function. So the constant of integration you add, you write it as a function of y. Number 3, differentiate the result in step 2 with respect to y. So remember initially, from this first step, n is partial f partial y. So once you integrate equation for m, you'll get a function f, and then when you differentiate that function with respect to y, you get partial f partial y. So that partial f partial y is the same as n. So that's why we're equating the two. And then once we equate the two, solve for this constant, which is written as a function of y. Okay, maybe we can actually say solve for the derivative of y, the derivative of this function g. And then number 4, integrate g prime of y with respect to y to obtain an expression for g of y. In this case, you don't have to add a constant of integration. So we are only interested in the function itself, g of y. So though the integration is indefinite, but at this point, you don't have to add the c constant. So substitute g of y into the result obtained in step 2 for the function f of xy. Then the final result, a general solution, is written as f of x comma y equals to c, where c is a constant. So if you are given extra information in the problem, you can as well find the value of that c. So number 7, if you are given initial or boundary conditions in the problem you can solve for C to get the specific solution. Just note that you can as well repeat this process by now in step 2, instead of integrating m with respect to x, you integrate n with respect to y and follow through the same order. So if you can actually revert the same process by now, starting with n, you will still get an answer to the differential equation. So the next session we'll discuss now examples on how to solve exact differential equation following these steps we have given in this class. Thank you.